have Dr. Jay Wang, who's professor in the Department of Civil Engineering at Louisiana Tech University. He's conducted extensive research in geotechnical engineering and finite element analysis. His areas of expertise include pile foundation engineering, soil structure interaction, pore water, soil interaction, and slope stability analysis. Dr. Wang has made significant contributions to predicting pile setup behavior and identifying the failure mechanisms of the levee breaches in New Orleans during Hurricane Katrina. In recent years, his research has focused on developing design criteria for highway embankments and containment dikes reinforced with geosynthetics under localized wave forces. Also, investigating the effects of expansive soils on pavements and shallow foundations, and evaluating the erosion resistance of vegetation in relation to wetland loss in Louisiana's coastal region. Dr. Wang places strong emphasis on the practical implementation and applicability of his research findings, and today we're going to be learning about wave impacts on highway embankments due to hurricanes, tropical storms in coastal Louisiana. Without further ado, take it away, Dr. Wang.
Thank you so much for the introduction. I really appreciate the complimentary words. My name is Jay Wang. I'm working on geotechnical engineering for a long time, and also I'm a registered engineer in Louisiana. So I keep my eyes on the engineering research, which will be practical, implementable, and feasible. So today, my presentation is related. The materials I'm going to present are related to wave impacts on highway embankment. Thank you. Everybody here, the attendees, my colleagues of engineers are working in industry for many years. So they get lots of practice on how to design highway embankment specifically in coastal area. And everybody understands, so highway embankment is such a critically important, which is the last barrier to protect the land area, the settlement area. And on the right, you can see the screen. This is a typical highway embankment. Left-hand side is the sea level, and we have to design safe highway embankment first. And this failure mechanism against tropic storm and hurricane are very complicated. We try to
Dr. Wang, yes. I'm sorry to interrupt you, but we still only see the first slide. So I don't know if you were supposed, it sounds like you were on the second slide.
This is the first slide.
Oh, I think we're on the title slide, so we don't see any images if you were alluding to any images.
This is because this is the first, this is the second slide.
Yes, we only see slide 1 currently.
How come? Yeah, because now we are already down to the second slide.
I think if you go to presentation mode, I think by pressing F5 on your keyboard, there we go. There we see slide 2.
So just go this way. Let me just go this way. I'm sorry. Yeah. This is the second slide. I'm sorry, my colleagues. Everybody can see the second slide.
Yes, correct.
Okay. So we have to design a highway embankment against the hydrodynamic forces, erosion, and a lot of things, as we can see here. So wave forces is the first impact when you come up to design embankment. So how the highway embankment in coastal area, the failure mechanism. So at the very beginning, I like to present some cases, and also we can summarize from these cases and with some lessons. NOVA, everybody familiar with NOVA? We get incomplete with probably this data not so incomplete. We just recently we check from online, we find from 1980 to 2018, this is almost 40 years, we get 233 disaster cases. And NOAA gets statistics. So a total of 23 weather climate disasters, and each case, the loss is more than $1 billion per event. And also we get some FEMA data we summarize here. Since April 30th, 2018, total cost for this FEMA recorded cases, the disaster cases, exceeds $1.5 trillion. And since 1978, the total cost is $57 billion for the 118 significant flooding events. This is the flooding events. In Louisiana, because we focus our research on Louisiana system, the Louisiana coastal area. So among these 118 significant flooding events, 9.3, almost 10% took place in Louisiana. Here, because there are lots of tons of cases, the failure cases because of hurricanes, storms. Here, I just pick up some examples, the cases tried to share with my colleague engineers. This is one example for Route 30, US 98 in Florida, which happened in Hurricane Dennis in 2005 during Hurricane Dennis. So totally this highway, the coastal highway, damaged for as long as 14.6 miles. Major damaging factor in most cases for this 14.6 miles, we get overtopping, we get a wave action. The wave action primarily dynamic forces, and then cause erosion. So another lesson we can learn, this is the Minnesota trunk highway, TH220, north of Oslo. And the same reason, because hurricane come over and the wave overtopping. But this time is not upstream damage. And obviously, so we get lots of damage downstream slope. So you can see once overtopping happens, so downstream get lots of damage because of erosion. So it happened in a downstream stage. This is the Louisiana State Highway 82, which damaged it during Tropic Storm Chris 1982, Hurricane Chantal and Jerry in 1989. So we get a wave impact, we get a wave overtopping, and at the toe of the embankment, we get a soil scouring. So hydrostatic pressure-induced slope stability is another issue we have to pay attention to. The impact, the Gulf of America. So the Gulf side lane destroyed in multiple storms with State Highway 82. So lessons we learned from this highway damage, State Highway 82 is important. Is wave impact. The important lessons is wave impact, and we should have design and construct adequate revetment weights, and also we have to consider permeability issue. And on the land side, we have to also protect the slope protection. So the common sense tells us we just pay special attention to the upstream, to seaside, but the land side slope, we have to pay attention how to protect the landslide slope. This is Texas State Highway 87. Bolivar Peninsula. So this is a famous peninsula. I think most of you know that. With Hurricane Ike in 2008, so a storm surged during the Hurricane Ike, and the wave impact eroded the embankment and completely washed away the roadway. So this is a very serious disaster. And many sections of this highway are washed away, and the long-term closure of this road. What are lessons we can learn from this disaster? Coastal highway barrier spillage are highly vulnerable to breaching. And this is the image, the air image you can see. Very similar thing we can find from these different disasters. This is probably the last one I like to share. Thousands of disaster examples like this, but here I just want to draw your attention. So how important to design the coastal highway. This is the last one. So we have, this happened a long time ago, US Highway 90. So we have in Mississippi. So we get more than 20 feet storm surge combined with powerful breaking wave impacts and also overtopped on seawall. So seawall is strong, but not strong enough for this. And also after going over the seawall, very severe scouring happened. The impact is pavement collapse and the disrupting of travel lanes on this critical coastal highway. And the lessons we learned almost the same thing. And here, even we get the seawall overtopped, and still this is well armored shorelines, but still not safe finally. So from all these lessons, we can see how to design a coastal highway embankment. So here, this is the points. We have different ways to design a highway. But all these different ways have to pay attention to withstand the wave action, storm surge, and erosion. So this is typical serious problems that we have to pay attention to. And the coastal highway usually built on soft clay, soft beach sand, very loose beach sand. So site investigation, site reconnaissance, also very serious. The CPT, SPT site investigation, we have to perform to get exactly soil data. So before we do design and do construction. So we have, in relation to our research, so I have to highlight the wave action, sea level rise, and the potential erosion. So this is a typical serious problem. We have to pay special attention to it. Coastal highway, we said we have to design and construct revetments or sea walls, and also we can grow vegetation slope, and for this specifically area. Another thing I like to highlight for coastal highway, because now geosynthetic materials spread out used everywhere in civil engineering. So geosynthetic material are often used to reinforce the embankment. And this reinforcement, this geosynthetic reinforcement can increase the soil shear strength and also reduce the settlement, specifically a highway built on soft soils. When you come to design this highway, this is a key considerations when you design the highway in coastal area. First of all, everybody understand, everybody agree with that slope stability issue. So we have to build a very safe highway, and with the factor of safety go beyond the minimum required factor of safety. Wave action, so this is the thing our research focus, the point our research focus. So wave action is not only hydrostatic water pressure. So if you design any inland highway embankment, you just consider the hydrostatic water pressure. But the coastal highway, you have to consider hydrodynamic pressure. And because the tropic storms and hurricanes come over, and so everything is not static and should be hydrodynamic. Another important thing I like to draw attention, I'm not sure this is the right way, but this is my own point. If you sort of disagree, that's fine. Sea level rise, this is the fact, so we cannot ignore it. So sea level rise and storm surge. And then we design this embankment highway, so the crest level should be getting higher and higher. So this we have to pay attention. So sometimes the design manual, we follow the traditional design manual, and it's not enough. So this is the thing I like to say. And this is one thing definitely I want to draw attention from audience. Soil properties already mentioned, the highway embankment built along the coastal area, underneath, and lots of soft soils and loose sands, soft clay. So soil properties have to be carefully investigated for site investigation. And the foundation evaluation, we already said we have to use a very practical SPT-CPT to get this soil properties, more accurate soil properties. Overflow design, this is related to hydrodynamic force, wave surge, and erosion problems. This is a very serious problem. Now, lots of people are doing research, but to be honest with you, as a professor and as an engineer, I don't think so far we get a very well-developed methodology which can be practically used in engineering for highway design. But lots of empirical methods already developed, already used in engineering practice. So this is a specific design approach. We got protected embankments, and we got unprotected embankments. For protected embankments, this is a traditional slope on upstream and downstream. And unprotected, and this slope on the seaside and on the backside, on the land side, sort of different. This is just a general thing, a traditional use by engineers for engineering practitioners. Here, I just tried this second time, I like to highlight the geosynthetic reinforcement. So geosynthetic reinforcement used everywhere, specifically the highway embankment. So this geosynthetic reinforcement can be used to increase the shear strength of the soils, and also can reduce the settlement of the highway. Another very practical use is piled embankment and stone columned embankment. This is a very practical for engineers. Erosion control mass on seaside. So a lot of things. Louisiana CPRA, the Coastal Protection Agency, this is a state government agency. They try to use artificial concrete mass put on the seaside to reduce the erosion things. So lessons we learned. So first we have to get the accurate wave and the surge data. So this data very important. And this is the thing at the very beginning before we start up working on SPTC funded research. And we keep in mind. So we have to get the wave data and the surge data. This is the one thing. And also we have designed a highway with adequate freeboard. But without data, we cannot say, so what is the accurate freeboard? So this is based on the wave and the surge data from different monitoring stations. Later on, I will show you what type of monitoring stations, what monitoring stations we used the data from. Landside protect. So we, as I mentioned just now, we try to protect landside. We try to protect the upstream, the seaside, but sometimes we pay less attention to landside because once the surge, wave surge overtopping embankment, and the landside will get eroded. Soils on the land side will be washed away. So this is a very, very important thing. The barrier spit vulnerability. This is the thing I think everybody understands. The last, not the least, is the regular monitoring and the maintenance. We get the data, and then we can find this data and use this data to do the design work. So when we come up to design embankment, so we go step by step. The first thing, we have to calculate wave forces, not only hydrostatic wave forces. And also we have to select the proper embankment fill material. And also we use the geosynthetic reinforcement. We apply application of environment control measures. And we cannot only do static analysis, we do dynamic analysis. These wave forces, we have to calculate the wave pressure just now, as I said. Wave run-up overtopping, this is the erosion problem, the toe scouring, and the storm surge and the wave action, and cyclic loading. So this is all the factors when we come up to design highway embankment. So it comes down to the point our research. As a professor and also as a registered engineer, I always remind myself. So we try to make our research as practical as possible and as implementable as possible. So we have to get the hydrodynamic force which applied on embankment. So we have to calculate this dynamic force first on embankment. And then with this hydrodynamic force applied on embankment, and then we try to find out what is the worst condition for the embankment. Usually we do the hydrostatic analysis, and we never consider the rapid drawdown or rapid failing. But during our research, we find the rapid drawdown case is such important, and in many analyses we already finished. This rapid drawdown case is the worst one. So this is the thing we already finished. Actually, this part of the work, this part of the research is not for cycle 1. Is partially is cycle 2 research. And also we already finished, but this research is still in progress. It's about geosynthetic reinforcement design. This is the second part, the cycle 2 research, but not finished yet. But I like to share some information and preliminary research achievements. So here, this is the comparison between conventional design and the modified design method we proposed. So traditional design of highway embankment, so we just do static analysis. We put the highway on the soft soils, on the coastal soils, and with the gravity, and then we calculate the settlement. We do the slope stability analysis. I think that's it. But for the introduced method, which we proposed, this is not finished yet. This is a few steps of research. So first, we do significant wave height analysis to calculate the hydrodynamic force. And then we do the very practical, implementable drained, undrained analysis, because this is software is already available. It's like a slope W, SEEP W is available for every industry company. So with this SEEP W and the slope W, and we find the worst case. And so far we find the rapid drawdown is the worst case. And we are trying to find industry partner and how to implement the method, design method we proposed. So it will be great if the colleagues now, as the audience, if we're interested, we can do collaboration in the future. It will be so great. And for the proposed design method, as we said, we have to find the wave height data first. And then we do hydrodynamic force calculation. And then we do the modeling. This modeling is not a research-based modeling, it's application-based modeling. We use the commercial software and do to find the worst case for long-term and short-term. And then we do the analysis for reinforcement. We try to find the reinforcement length and spacing. This is for the geosynthetic design part, which is ongoing and we haven't finished yet. So first, how to find out the sort of the first part of the work, determination of wave height. Lots of scientists, lots of mathematicians try to use the fluid dynamics based numerical model, say like the Delft 3D model. They use the powerful computer and to calculate. This is just a purely theoretical research. This type of research we did a long time ago, but when you do the numerical modeling, so we have to be very careful at the very beginning, the initial data input and boundary condition data input. If we couldn't input the correct results for initial condition and boundary condition, sometimes engineers definitely every engineer knows we got the garbage in, we got the garbage out. So sometimes, because I'm running the numerical modeling for more than 30 years, so I know what's going on. So, and also it's so complicated. I don't think engineers in engineering practice like it. So in this research, we try to avoid any fluid dynamics based finite element analysis. We never did that. We just based on the monitoring station. You see the Gulf of America, we get lots of stations. You see from this screen, we can see the lots of monitoring stations provided by NOAA. And also we have different sources, NOAA, and also different sources of data. But one thing, unfortunately, this data systematically we checked only happens between this is the systematic data we only get for the last 20 years. We don't have the data like for last 100 years. Some individual hurricanes we get some data, but only we get 20 years data available from online. And here, this is the 13 monitoring station from NOAA and the USGS wave monitoring station just around the Gulf of America. So we have 13 monitoring stations. From these 13 monitoring stations, we get data. So the data, the time spans from 2004 to 2024. So this is a 20-year data. So if we get 100 years data, and this will be fantastic. And with this data, we do the statistic analysis. You see on the left, the figure on the left, and you can see this data plotted, just directly plot this data from these 13 monitoring stations. And on the right-hand side, we get the data from the highest wave height from different monitoring stations. So this is only the original data we inherited from NOAA and the USGS. This data we analyzed using some tools, the statistic tool we call GEV. So this is a generalized extreme value analysis model. So we do some statistical analysis, and then we analyze the wave height for different return periods, say 5-year return period, and 15-year and 20-year, because we have only 20-year wave data. So now we just got the data for 2-year, 5-year, 10-year, and 20-year return periods. And also we confirmed this GEV model and the empirical model. So this is statistic analysis, I think, reliable from the two figures we plotted. Yeah, we get some. The statistic analysis is not so hard, yeah, but the details, I just try to skip the details of the statistic analysis. This slide shows this data, the data analysis, the GEV model is reliable. Because this is 13 monitoring stations scattered along the coast of this this Gulf of America. But for some area, we don't have monitoring stations. And then we try to find, so how to interpolate this wave heights. So we get another software we call the ordinary Kriging method. And this model, this statistic-based model, we can do the spatial interpolation. So for any area where we got no monitoring station available, and we still can get the wave height data. So everything I try to draw attention again from the audience. So this all this analysis, all this wave height, no numerical modeling data, just from monitoring stations. So this is the real data, the real high wave height data. And also we did some critical conditions. And everybody knows if you work with a coastal highway embankment design, we have two types of wave. We have breaking wave or we have non-breaking wave. Right here, you see at the 13 monitoring stations, almost everywhere, the wave, breaking wave. The breaking wave are most risky condition compared with non-breaking waves. And in engineering practice, no matter is it the U.S. Army based method or any other method, we get lots of empirical methods. In cycle 1, SPTC sponsored the cycle 1 research. We compared the multiple equations. These equations come up. We compared the results, the outcomes from different empirical equations. We find this typical two methods give a very conservative results. Minikin and Blackmore, Hosan, these two methods give the results very conservative. As an engineer, so I say we try to find the most conservative wave heights to do the analysis. On the right, on this slide, on the right, you can see corresponding to different empirical methods. And we have the hydrodynamic force calculation formula. This formula is very simple. This is developed by engineering practice, like U.S. Army Corps of Engineers, that they worked on design and the construction of a coastal highway for many years. So this is the results come up very reliable. And we pick up two spots in Louisiana. One is the east side is the New Canal station. The other one is Lake Charles, close to Lake Charles. The station was close to Lake Charles. So from here, this is a calculation following the two different empirical methods. This is the hydrodynamic force we calculate, this is a distribution, the pressure distribution on the embankment. This embankment is a virtual embankment. This embankment close to New Orleans is close to the New Canal Station. And the other one, as I mentioned just now, we have virtual embankment near Lake Charles. And we selected the 20-year return period wave, hurricane or storm, and we use the Minikin plus Blackmore and Hosan wave pressure distribution method, and we calculate the wave distribution. So this is the first part of our research goal. So here is the example, because at the very beginning, we have we already mentioned Highway 82, state Louisiana Highway 82 got real damage in previously. So we try to use this the developed methodology to analyze or design State Highway 82. State Highway in southwest of Louisiana in Cameron Parish. This is a 2-lane asphalt road. Is the only east-west road in the area. So it's very critical, important if we take hurricane evacuation, and this is the only roadway we can use. So this is critical, important, but previously it was severely damaged. So how to implement the new design methodology? So this is what I like to say a little bit more about it. you see this is the road of Highway 82, and on the right, this is the SPT soil profile we get. We have moisture content on the left, and in the middle, this is the undrained shear strength. And on the right-hand side, this is dry unit weight. This is soil profile of the highway, Louisiana State Highway 82. So you see from this profile, we can see the embankment is clay soil, clay filling, and then right below the embankment filling, fill, we get everywhere. We get soft clay, we get a sealed clay. So everything is so soft, so we have to pay attention. And also, this highway is in extreme southwest Louisiana. So we find the extreme wave height. This wave height, we follow the method just now I mentioned. We do the statistic analysis. We find the wave height for return period 2, 5, 15, 25, 50, 100 years. For 50, 100 years, as I mentioned, we don't have lots of data. So this 50, 100 years data probably not so reliable. Yeah. And we follow the U.S. Army Corps of Engineers method. We calculate the hydrodynamic pressure. And also, we said in the proposed method, we have to do long-term stability analysis. And for conventional method, we just do statics analysis for drain condition. But we already calculate the hydrodynamic loading. So, and at this moment, once we come up to analyze the slope stability, we do hydrodynamic loading analysis. So we find the critical factor of safety. And also, as I mentioned, this is a very important finding with the research for cycle 2. The short-term stability, the rapid fading, drawdown, this is a critical condition. This is on-drain analysis. We have to pay special attention. So from here, I just showed some typical results. The factor of safety is very critical. If we use, this is another, the more concrete results for a rapid drawdown methodology. So it's a critical case for the on-drain analysis. At the very beginning, if a hurricane comes up, the sea level rise, and the hurricane is receding, and then sea level will draw down. During this like a 2-hour rapid drawdown or 3-hour rapid drawdown, the factor of safety on the highway embankment will keep on decreasing. You see here, this is the typical graph we can see. So for the hydrostatic condition, typically is not the controlling condition, not a critical condition, but the rapid drawdown is a critical condition. And here we just compare, there are two methods. On the top, we have the static conventional method to design the highway. We do the slope stability analysis, and we didn't do the seepage analysis. We find the factor of safety using conventional method meets the minimum requirement. It's safe. But if we use the new methodology, you can see corresponding to the rapid drawdown case, the factor of safety is critical is from 1.26. This data I will try to see the difference between conventional method. So I keep the 3 digits after decimal points. So from engineer's point of view, it doesn't make sense, but I just want to show the difference. Okay, if we follow the new methodology, and then we have the factor of safety significantly reduced. And this table, you can see if we follow the conventional method, we already said if for the regular wave loading condition without wave, just the sea level water pressure, we have the 1.5, but if we get the wave loading and 1.26, but if we apply the new method and using hydrodynamic force on it, and also we do seepage analysis, and then we pick up the rapid drawdown case, and then the factor of safety down to almost the critical point, 1.0 case. So this is a very important thing. And for the conventional method on the top, we can only use the one layer of geosynthetics, one layer of geosynthetic material, and then we can guarantee the highway embankment with a factor of safety of 1.6 is greater than the required minimum requirement is 1.5. But if we adopt the new method, we apply hydrodynamic force, we have to use 7 layers of the same geograde reinforcement, and then we can guarantee the factor of safety is 1.5. So you see, this is a big difference if we follow the conventional method, and then if we adopt the new method. Geosynthetic method, or my colleagues, the audience, I think you guys are familiar with that. We follow the traditional way. This is FHWA adopted the design manual. We pick up spacing, we calculate the spacing, and for different embankment height, and we also find the critical length for each piece of geosynthetic material at different elevations. So that we have 2 steps. Step A, we find the spacing. So this is the traditional way to find the spacing. So if you follow the FHWA adopted design manual, so this is the method. This is the calculation. It's a design method, design calculations. Step B, step 2. So we have to determine the reinforcement length. The reinforcement length, we have 2 parts. We have effective length, we have resisting length. And now the research is underway. We try to integrate the new methodology, the new idea at the very beginning I already mentioned. We have to consider hydrodynamic force, and also we use seep W plus slope W to identify the critical case to determine the resisting length. So once this part of the research is done, so we can propose a systematic method for coastal highway design, how to say implementable coastal highway, a reinforced coastal highway embankment design methodology. So hopefully this method will come up complete very soon. But this, as I mentioned, this part of research is incomplete. So I just want to present some partial way. This is another incomplete result I like to present. So from here, from following the new methodology, and we can say the critical case for Highway 82, Louisiana State Highway 82. The critical case is after hurricane receding, the rapid drawdown situation is the most critical. So based on this critical, we try to find the spacing and the length. This is some idea I like to share. We have tried to use parametric analysis to find out the resisting length of geosynthetic, geogrid, or geotextile. We will get some new idea. We will integrate some new idea to find the resisting length. This is part of this is the second part of the entire length of geosynthetics. So I like to make a summary. This presentation presented the results, achievements, which we think very practical and implementable and also feasible for engineering design, specifically design a coastal highway. And this coastal highway, we cannot simply follow the traditional method. We just do a hydrostatic analysis, and then we determine the height and the slope stability analysis. So we have to use the new methodology to find. First step is find the wave height. So how to find the wave height? We don't follow the scientists, mathematician recommended method. Say we do the Del 3D analysis, or we do some other very theoretical fluid dynamics based numerical modeling or finite element modeling method. But we follow the data. We do the data analysis. This wave height data recorded by lots of monitoring stations. These monitoring stations specifically built in the last 10 and 20 years by NOAA and the USGS around Gulf of America. So we use a different methodology, say GEV, a statistical analysis, or creating a special interpolation method to find the wave height at a different area. So you design the highway for different local area. Even though we don't have the monitoring station, we still can find the wave heights corresponding to different tropic storms or hurricanes with a return period, 5-year, 10-year, 15-year, or 20-year. Later, if we get more data, and then we can extend it to like a 50-year, 100 years. So this is the advantage we can take from this monitoring station data. We choose the empirical formula to calculate the hydrodynamic force. This hydrodynamic force applied instead of hydrostatic water pressure applying to highway embankment. And also, we have to do seepage analysis and the plus slope stability analysis. We find the critical case. So in many cases, so far we analyzed the rapid drawdown. So right after hurricane or storm leave from this area, this will be the most serious case we have to consider when you come up design this highway. As I mentioned, the new method is undergoing, is under investigation. We don't have a complete result yet. And this is the last thing, not the least thing I like to appreciate. So far, the research achievements I presented here funded by this research projects funded by SPTC. So without funding opportunity provided by SPTC, we cannot carry out this research. Another thing I like to appreciate my graduate students, Abhishek and Uday. These two gentlemen working so hard and implement the research ideas we have. So here, this is my presentation. So I don't know here. There are questions from audience. I like to take this chance to apologize again. So at the very beginning, we get sort of messed up because at Louisiana Tech, we always use Zoom meeting, the tool of Zoom meeting. So I'm not familiar with the Microsoft tool.
All right, thank you so much, Dr. Wang. That was an excellent presentation. Again, if you have any questions, please feel free to type them in the chat, or if you'd like to ask them verbally, you can raise your hand and we can call on you that way. So please, the floor is open if anyone has any questions. 10 minutes for Q&A. All right, it looks like we one hand raised. Yes.
I'm sorry, I couldn't hear.
Yes, you can unmute yourself, Marilyn, and you can ask your question.
Yeah, thank you. Yeah, Jay, this is Murali from OU. Thanks for interesting presentation. Very thorough in all aspects. Yeah. Couple of quick questions. One is general.
I'm sorry, it seems the disconnection come up.
Oh, okay. Yeah, that was a beep. Somebody leaving probably. Okay, so general question. You using the wave actual measurements makes a lot of sense. But and climate change and all of them, because the past measurements are not indicative of what the future would be, right? So that's my general question. Let me ask the second one and then you can answer both. The next one is in your slide 40. I wasn't sure whether it was a typo or not, but your factor of safety seemed to be higher with the hydrodynamic forces than without them. Yeah, that's it.
Yeah, this is things we discussed. We will try to, I discussed with graduate students. This is 40, is right?
Yeah, slide 40. Yeah.
Yeah. Okay. Yeah. We noticed this problem. I checked with my graduate students for this case, and we said if the sea level rising, and then I let my graduate students check the factor of safety for both. Say the potential slip surface is on the seaside, and also I like to check with. I like my students to check if the potential slip surface from seaside to land side. And because this highway embankment is very wide, they said still the seaside factor of safety is the controlling point. So if you get a sea level rising on the seaside, and this water pressure, water force will push against the landslide to happen in for this potential slip site. So the potential slip surface from the seaside to land side is not a controlling condition. But as this is a good point, I will double check with my graduate student, let them analyze the potential slip surfaces, which start up from seaside to the land side. See if the sea level rising or hydrodynamic force applied, and what is the factor of safety exactly for different type of critical slip surfaces. They already checked. They said the factor of safety from seaside to land side still greater than the critical condition. Just now, I demonstrated on this slide. Yeah, this is definitely a good point. Yeah, from the common sense, if water level rising, the factor of safety should be getting smaller. But after analysis, it turned out the results go this way. Yeah, I will double check with my graduate students. Yeah, this is a good point, definitely.
Yeah. What about the other question about how are you going to predict the maximum water heights in a changing climate?
This is probably out of the research area, because we just got data from these monitoring stations. So climate change and then water level definitely will, the seawater level will rise, but we don't know exactly. So the design methods just following this proposed design method, we just follow the data we get from this 13 monitoring stations. To be honest with you, the second question, I couldn't tell you exactly what's the solution to your second question.
Okay, that sounds good. Thank you, Jay.
Yeah,
nice presentation.
Sure. Yeah.
All right, we have 5 minutes left. Does anyone else have a question? Again, you can either type it in the chat or you can raise your hand and I can call on you. As we wait for a question, Dr. Wang, is it all right if anyone has a question afterwards? Is it okay if they email you that question?
Sure. Yeah, absolutely. Yeah. I can answer the questions right after I received them, and then I respond immediately after I get them.
Okay, perfect. All right, last call for questions before we wrap things up. All right, well, I'd like to give a virtual applause to our presenter, Dr. Wang. This was a fantastic presentation and very illuminating on this topic. We thank you so much for participating in this. For our speaker and all of our attendees, excellent job. This will be recorded and posted on our website at SPTC.org. We'll be sending out a survey to all of our attendees to see how we did.
Thank you so much. Thank you.
Oh, thank you. Yes.
So for SPTC, yeah, and thank you for the audience for your patience.
Yes, excellent. Yeah, we made it in good time as well. So kudos to you, Dr. Wang, for the excellent presentation. We'll be sending out professional development hours probably in a week or 2 weeks from now. So stay tuned for that. And again, one final applause for Dr. Wang. Excellent job. And we look forward to seeing everyone next time. Thank you again.
Thank you. Appreciate it. Bye.
Take care. Bye.
Bye.